So for my next video in my series on my 5-finger code finder door opening robot that can open many Ford car doors in less than 11 minutes and usually more like 4, I wanted to discuss what makes this thing so quick about unlocking a door. So to do that, we're going to compare to something you're more familiar with. We'll take a step backwards and look at the 10-key keypad you might be more familiar with from a security system or the keypad you stick on your garage door to open your garage door. Well, you have 10-digit choices for each digit. We'll go with a 5-digit code just to compare to Ford. So your choices would be from 00000 to 99999. It's 100,000 combinations. Now to get that 100,000 combinations mathematically, you just multiply how many choices you have for each digit here times the 5 digits. So 10 to the 5th power is 100,000 different codes, which is obvious since we're all familiar with decimal numbering, but I'll come back to that in a minute when I'm talking about the 5-key keypad. But with 500,000 key presses, because there's 100,000 codes and 5 digits, my robot here would take 28 hours to actually finish all of that. But Ford didn't go with the 10-key keypad. They went with a keypad that only has 5 keys. So we have 5 choices for each digit times 5 digits. So you compare that to my multiplying the 10 choices out 5 times for each of the digit and getting 100,000 codes. Here we only have 5 times 5 times 5 times 5 times 5, 3,125 codes. That's only 3% as many codes, a 97% reduction. So why would Ford do something that reduced the number of codes by 97% and reduced the security by 97%? Well, probably because a big 10-key keypad like that on your car door would be ugly and it would be more expensive. People wouldn't want it. And they probably figured 3,125 codes is probably enough. So that's the first thing. Second thing that makes this so easy is what I call the shift and check again principle. Every time you press a key on one of these Ford car doors, it rechecks the code with the previous 4 digits you entered plus the button you just pressed. So basically it's dropping the oldest digit, shifting the others over one, and adding the one you just pressed to the end. If we go back to a traditional system where you have to enter every code in full, to check just these 5 codes, 111111 up to 11115, you would actually have to press 25 key presses to check those 5 codes. So to check, say, all 3,125 codes, you'd have to enter 15,625 key presses. But with their shift and check system, let's take a sequence like this where you got 1935119371119. You enter that because it's checking on every digit. Well, first you got to actually get 5 digits in before it does the check. So the first code it checks is the 19351. But as soon as you press this one here, it rechecks the previous 5, and now you've checked 93511. You enter this 9 here, and now you've checked 35119, and so forth, then 51193, and 11937, and so forth. So you can enter this whole sequence here, and you've only pressed 12 keys, but you've checked 8 codes instead of the 40 keys it would check to enter, 40 keys you'd have to press to enter all of these numbers. Because after the first 4 digits, you're checking a 5-digit code in every single key press. So all we have to do to make this quicker and easier is if we can find an optimal sequence of numbers where we are checking a new code on every single key press, we're reusing the previous 4 digits for every code, we're not wasting any key presses on codes we already checked, we can drastically reduce the time to test all these codes one more time. But first, why would Ford use this shift and check on every key press method when it reduces the security even more? Well, it's to make the system easy to use when you make a mistake. Say, what if they only check digits in groups of 5, and your code is 1, 2, 3, 4, 5?
That's amazing. I've got the same combination on my luggage.
If you make a mistake and say enter 122 and then you stop because you realize that's not your code, you made a mistake, and then you start over and you enter 1, 2, 3, 4, 5, what you've really entered is 122, 1, 2, 3, 4, 5. If it waited for you to finish 5 digits to check a code, what it would check is 12212. And then it would be sitting there waiting with the 3, 4, 5, waiting for 2 more digits to check the next group of 5, and it would completely miss that you entered 1, 2, 3, 4, 5. So to make this work as you would expect it to work, they have to check on every key press. This is partly because they don't have a cancel key for you to press when you make a mistake. They don't have an enter key to press to tell it when you're done entering a code. So they have to check on every button to make it actually unlock when you enter your code properly. So back to what I said before about finding this optimal sequence that doesn't waste any key presses and doesn't waste any time. It turns out that mathematicians have already done this for us. There was a mathematician named Nicholas DeBruijn, who lived from 1918 to 2012, who came up with a thing that got named after him called the DeBruijn Sequence. And this is stolen right from the Wikipedia page. It says, in combinatorial mathematics, a DeBruijn sequence of order n on size k alphabet A is a cyclic sequence in which every possible length n string on A occurs exactly once as a substring, i.e. as a contiguous sequence. Such a sequence is denoted by bkn and has length k to the n power, which is also the number of distinct substrings of length n on A. DeBruijn sequences are therefore optimally short. By optimally short means that it's exactly what we're looking for. We're not wasting any time on anything. So yeah, I had to read that like 10 times to really figure out what they meant by that, but it's actually a lot simpler than it sounds. Alphabet is simply the symbols that you can use in your code. So for the Ford keypad, our alphabet is 1, 3, 5, 7, 9. For our 5-digit keypad, it says size K alphabet. So the size of our alphabet is 5. We have 5 letters in our alphabet. And length n string is the length of our code, which is 5 digits. So if you go back up, it says the sequence has length k to the nth power. So the number of digits in the sequence is 5 to the 5th power, which is 3,125. That's the exact same number of digits as we have for a number of codes on our keypad. So this is exactly what we need to enter all the codes with the least key press as possible. Now it turns out in this keypad system, it actually takes 3,129 key presses because the first 4 you enter don't actually test a code because you haven't entered a 5-digit code yet. So to actually make it work properly and test those first 4 digits, I have to put them back on the end of the sequence. It's kind of like you're going around in a circle. If you know on the Wikipedia page, it says it's a cyclic sequence. So if you look at the Wikipedia page, they have a little piece of computer code in a language called Python, which I really haven't used before, but it's pretty straightforward. I was able to adapt it to my needs. This is the piece of code. It generates a sequence, and I modified the code right here to put a comma and a space between each one so that I could cut and paste the result into the Arduino code for my gadget here so I can use it as an array declaration. Here I put in the alphabet, which is simply 1, 3, 5, 7, 9, the numbers on the keys. I'm ignoring all the even numbers because they're just on the same keys as the odd numbers. And 5 here is the length of the code. So this just generates the whole sequence for 5-digit codes using the numbers 1, 3, 5, 7, 9. I cheated a bit and took the commas back out to show you this. This is the entire sequence printed on one piece of paper. You enter this, and you will unlock your door somewhere along the way here. So let's put this all together and show how this drastically reduces the time required. So my robot can press 5 keys per second, but if we were back on that normal 10 keypad with the 5-digit code and had to test everything the hard way, entering each code in full, that'd be 100,000 codes, 5 digits each, 500,000 key presses, divided by 5 presses per second, back to 100,000 seconds, but that's 28 hours. But with the 5 keypad and the 5-digit code, if we still had to enter each code in full, that would be 15,625 key presses at 5 presses per second, or back to 3,125 seconds, which is still 52 minutes. But the final piece of the puzzle, this checking every digit as a 5-digit code with the previous 4, and using the DeBruijn sequence where we don't waste any time rechecking, wasting digits, rechecking codes we already checked. We can do this in only 3,129 key presses at 5 per second in 626 seconds, and we can unlock the door in 10 minutes and 26 seconds. Now, on average, it'll be a lot quicker than that because there's actually 2 codes it can find. It can find your your user code, if you want to call it that. It can also find the factory set code. Every Ford vehicle has a factory set code that you can't change. So there's actually 2 codes it can find. And so what happens is, in this big long sequence here, there's actually two numbers in here somewhere that you can find to unlock the door. So on average, it takes about 1/3 of that, 10 minutes and 26 seconds. So we're talking, like less than 4 minutes on average. So what do we learn from all of this? Security is always a lesson in compromises. Ford went with a 5-digit keypad because 10-digit keypad would cost more and it'd be big and ugly. Nobody would want something like that hanging on their car door. They checked the last 5 digits entered every time you press a key. They needed to do this for usability because there's no way to cancel a partially entered incorrect code and start over. There's no cancel key, no enter key. So they had to do this to make it work like people would expect. Now, it kind of sounds like I'm complaining about Ford and their security here through this whole video series, but I'm not really. I think they did this exactly as correctly as they should have. These were compromises that were necessary to make a system that people would want and people would use, and a system that would work as people expect. So in security, compromises, they're often okay as long as you understand the trade-offs. So during the development of this system, I found out that Ford had already anticipated this. I developed it using my 2001 Ford Explorer, and when I recently traded up to a 2017 Explorer, in the owner's manual I found something called the anti-scan feature. And it says that the keypad goes into anti-scan mode if you enter the wrong code 7 times. So you only get 35 key presses, and then you're locked out for a minute, and the keypad flashes for that minute to tell you that you're locked out and you can't enter a code. Now, the manual says this feature turns off after any of the following: 1 minute of keypad inactivity, you press the unlock button on your remote control, you start your vehicle, or it says you unlock using intelligent access. I guess that means the wireless, the push button start wireless key fob. So that's interesting that they anticipated this, and it goes back to what I said about security being a lesson in compromises. It sounded like this was a big problem, but Ford found a simple way to fix the problem, because in reality nobody's going to probably enter their code wrong 5 times in a row anyway. So this prevents you from doing this scan feature and makes the system a lot more secure. So I guess that's it for this installment of the 5-Finger Code Finder project. Next time I think I'll make a video where I actually talk a little bit about how I built this, although it's not too hard, and maybe some ideas I had to actually make it easier to build if one of you wants to make one of your own. So stay tuned for that. And thanks for watching.